All right. So a couple announcements, mostly the same as last time. Homework 3 is due tomorrow, turned in tonight for bonus point. Have a new vitamin out, do that before Friday's lecture. So kind of the standard stuff. One thing that's kind of an update is that we've canceled the finish up labs that are on Fridays typically. And so if you were going to those, just please attend office hours instead. We just feel like this is gonna be a little bit better use of everybody's time and staff. So just small change there. But yeah, that's pretty much it. And then in terms of kind of weekly goals, so last time we talked about distributions, we talked about categorical distributions, we talked about numerical distributions. So today we'll just kind of review some of those things. There's a few things we didn't quite get to. We'll start talking about how we can write our own functions. So we've been using functions throughout the class so far. So today we'll talk about how do we write our own. And then going into Friday, we'll actually make predictions for the first time, which is exciting, and learn a few other functions related to tables. So you might see there's a few more here that mention group, pivot, join. So these will be kind of the last few table functions we'll probably be covering before we're really kind of ready to dive deeper into the more like the statistical analysis portion of the course. Cool. So the main thing that we need to cover that we didn't get to cover last time is understanding the heights of histograms and how do you interpret that. So in order to do that, let's actually quickly review what we did on Friday, or sorry, not on Friday, on Monday, in terms of histograms. So we had this data set of all of the top movies up until 2017. So that's just top movies, 2017.csv. And so we read this in, always run the first line. Okay, let's try this again. Okay, so we had the data set. We've been using this now for like the last couple of lectures. So we've seen this one before. And so first thing we did was we read it in, and then we said, okay, we wanted to visualize a histogram, or the distribution really, of the ages of the movies in this data set. And so we didn't really have the age, we had the year that the movie came out. So then we said, okay, let's actually make another column that contains the ages of the movies. So first we made an array that has those values. So we're gonna name it ages, and we said ages is gonna be 2020 minus top movies dot column year. And so that is going to give us the age of the movies. And then we said, let's add this into the table as a new column. So we'll do top movies equals top movies column. And we're just going to call this age, pass in ages. And so now we have, if I just show you what top movies looks like, now we have this new column here called age. So now we have the age of the movie. So that's great. And now we're ready to actually look at kind of the distribution of the ages of the movies. And so we talked about how with categorical variables, it's kind of straightforward to show the distribution. You just kind of have to find all the unique values and then just count up how many times each unique value shows up in your data set. In this case, it's numerical. So you need a way to bin those values in order to count up how many times each individual shows up in one of those bins. And so typically you'll probably be using kind of equally spaced bins, but sometimes you might also use bins that are not of equal like width. And so we had an example of that. And so I'll just kind of add that back in here again. So we made it this set of bins. So we had 0, 5, 10, 15, and then it went to 25, 40, 65, and 100. And so we specify our set of bins in an array, and this is something you would do every time. You could either use np.arange if you wanted to do that. And so once you have your set of bins, if you actually want to view the numerical distribution in a table form, you can use the bin function. So that's what we did last time. So we said, we're going to call this bin data. And basically what we do is we take top movies, we call .bin, and we say, what do we want to bin it on? We want to bin it on age. And what bins do we want to use? We want to use my bins. And so we can take a look at that. And so this is actually one way to visualize the numerical distribution of age. And so we have the bins on the left here. We have how many movies are in each bin on the second column. And then what we said was we wanted to also calculate the percent of data that is in each bin. So from this table, we know that the 0 to 5 bin has 12 movies, the 5 to 10 bin has 18 movies. So we know how many movies are in each bin, but we just want to convert that into what percent of all the movies are in each bin. And so if you want to know that, for example, this first bin, 0 to 5, there's 12 movies in there. Therefore, the percent of movies that is in that bin is going to be 12 divided by the total number of movies. And the total number of movies is just the sum of this age count column, because these are just the counts of all the movies. So what we can do is, first of all, let's just verify what the number of movies is. So the number of movies is going to be the sum of bin data dot column age count. And then we can just show this value here. So that's 200. And so we said that if we want to know the percent of movies that's in each bin, we just need to take the count and divide by the total count. So let's actually make a new array for this. So we'll say this is called percents, and this is going to be bin data dot column age count divided by num movies. And so if we do this, sorry, typo, num movies. So if we do this and just take a look at this guy, we get the percents like this. So 0.06, 0.09, 0.085. So 0.06 means 6%, 0.09 means 9%. So basically, like the first 0 to 5 bin contains 6% of the movies, 5 to 10 bin contains 9% of the movies, so on. And we said, well, it might be nice to multiply this by 100 just so the numbers look a little bit more interpretable, because 0.06 means 6%. So let's just multiply by 100 so that this number is a 6 instead. And so that's why we multiplied by 100 here. And so bin data.column, I saw a question about this. What does this do? Bin data.column age count is going to take just this age count column and convert it into an array. And so once we have it as an array, then we can do mathematical computations on it. So bin data.column, I'll just actually show you what this has, so you can see it. So this has the data in that column in an array form. And once it's in an array form, then we can do things like divide by a number, multiply by a number. That's why we do that. So let's instead multiply by 100. So if we do that, now percents looks a little bit more easier to read. So now you can just interpret this as 6%, 9%, 8.5%, and so on. And then we said, okay, that's great. So now we know what percent of the movies are in each bin. Let's add that as a new column into the table so that we can kind of see everything side by side. It just makes it a little bit easier to visualize everything. So we said, let's do bin data equals bin data with column. We can add a new column now. Let's just call it percent. And then we'll put in percents here. And then let's actually get the value out. So now we have our table that we had above, but there's a new column here with percent. And so now if you wanted to interpret this, what this is saying is that 12 of the movies in data set are 0 to 5 years old. That makes up 6% of all the movies in our data set. 18% of the movies in our data set are 5 to 10 years old. That makes up 9% of the movies, and so on. And so in the context of a histogram, what does this mean? So let's visualize the histogram. So how we do this, we do top movies, and then we call the hist function. And the hist function, we pass in which column we want to visualize the histogram of. So in this case, we want to visualize histogram of age. And then we'll have to specify our bins. So in this case, bins are just going to be my bins, which is the same bins that were used to make this table right above. And then we just specify the unit just for clarity. And so now it's really nice to be able to see these together. So now what this is saying is that this first bin here, what does it correspond to? It corresponds to movies that are 0 to 5 years old. And that bin has 12 movies in it, which makes up 6% of all the movies. So that 6% equals the area of this bin. So remember, in histograms, area equals percent. So the area of this bin is 6%. Then if you go over to the next bin, we have 5, these are movies that are 5 to 10 years old, and they make up 9% of all the movies. So the area of this bin is 9%. And so basically the numbers in this column, in the third column, correspond to the areas of each of these. And so you can see like this really large one here that's 40 to 60, that one is 26%. So that's actually the biggest bin. That has the most movies in it. So that's kind of how we can interpret that. And then this last bin, which is like kind of really wide but not that tall, only has 9% movies. But it is quite a wide bin because it has movies that are from like 65 to 100 years old. And so there's some cases where you might want to have unequal bins, mainly because maybe there's not that much data. Like in this case, this is a really large range of years, like 65 to 100 years old. That's actually our widest bin. But there aren't that many movies in it. There's only 18 movies in that bin. And so if we had split this up into maybe like smaller bins or something, some of the bins, some of the histogram bars might have had like 0 height there. So sometimes it's a little bit easier to just visualize things like this. And so this is kind of what we had. This is kind of where we left off last lecture. And so the next question was, okay, so the area of each bin represents the percent of data that's there. The width of each bin tells us kind of the range of the data that that bin is talking about. But what does the height represent? You see this weird unit here, percent per year. Why is it percent per year, on that axis? And so the reason for that is we know that the area needs to have a unit of percent because the area is the percent of the data. And we know the width in this case is the year, how many years are represented in that bin. So for example, this is 40 to 65 years. And we know that kind of just from geometry that the area is always the length times the width. So in this case, the width is in years, and we know that the final result is in percent. So that means that the units that are along kind of the y-axis needs to be percent per year. And so that may not have made sense. So let me just kind of, I can write it out as well. But basically, I'll just write it as some comments here. So we know that area equals percent of data. We know that width equals years of our, kind of the width of our range. And therefore we know that, area equals width times height. So what does this mean? This means that height has to equal area divided by width, which implies that the units for height has to be percent divided by years. And so that's why we see percent per year. And so this just ensures that basically if you do take the width and you do take the height, if you multiply it together, you get something that's like something percent. That's the basic idea of why we do that. And so now we can actually use that information to try to calculate the height of one of these bins. So, a question might be, what's the height of the 40 to 65 bin? So we know that there's this 40 to 65 bin. And, as you mentioned here, the height is area divided by width. So first of all, we have to just figure out what's the area. So the area is the percentage that's in the 40 to 65 bin. So if we go up here to our table that we can see, what's the area of the 40 to 65 bin? Cool, yeah, so 26%. So the 40 to 65 bin is represented with this row here, and the percent of data that's in there is 26%. So we know that the area of this bin is going to be 26. And then the width of this bin, what's the width of this bin? Sorry, this should be like a closed parentheses or open parentheses. So the width should be 65 minus 40, which is 25. So we'll just have both of these written out. And then now if we want to know the height, we just do area divided by width. And we can show that value. So we get 1.04. This actually looks different than what I have here for some reason. It's a bit strange. Oh, I guess the percentages are slightly different. I'm not sure why exactly. But in any case, yeah, so we have 26, if we have 26% up here, and we have a width of 25, then 26 over that gives us 1.04. So what this means is that the height of the 40 to 65 bin is 1.04% per year. And so that would be kind of weird. Like, what does that mean? 1.04% per year. So one way to think about it is that the height basically measures kind of like density, or like almost one way to think about it is like crowdedness. So it's giving you a sense of like how many movies were there per year during that time span. So what this is basically saying is from 40 to 65 years ago, during that time period, there were, at least in our data set, there's the amount of data we're seeing there is 1.04% per year. That's just how many movies are there during that time period. Whereas during this time period, which is 25 to 45, there were a lot more movies per year, at least in our data set. So that's essentially what it's telling you. It's kind of like what's kind of the rate of movies that are coming out or something like that. That's one way to think about it. So it's just kind of the frequency of movies appearing in the data set. So maybe like we don't have a lot of movies basically during this time period that we have data from. And maybe there's like fewer movies that we have data from in this other time period, from 65 to 100. So that's kind of one way to interpret that. And so does this mean 1.04% of total movies? No, it's not total movies. It's just saying that that's kind of, well, yeah, actually it is 1.04% of total movies. That's how many movies there are there per year in that time period. So from the 40 to 65-year-old time period, per year in that bin, you will have roughly 1% of all the movies. That's how much is appearing per year. And so that's why it's kind of this sense of like crowdedness, essentially. So that's kind of how we interpret that. And so if we wanted to similarly get the heights of the rest of the bins, we could do this as well. So if we want to do the heights of the rest of the bins, let's call these like bin, actually, I think we'll probably skip that actually just for the sake of time. But let me go back to the slides. I'll let you guys try to do that. That is in the slides. But let's just review this, because actually this is a little bit more important. Just like figuring out how to do it for one bin. So again, in this case, we have 40 to 65 bin contains 51 out of the 200 movies. And so that's 25.5%. I'm not sure why we're getting 26 up here. Maybe there's like some strange rounding thing that I did by accident. But yeah, we have 51 out of 200, 25.5%. And then the width is 25 years wide. So then the height of the bar is just the area divided by the width. And so this is kind of the general way to calculate the heights in a histogram. Just take the percentage that's in there, that's in that bar, and then divide by the width of the bar. That gives you the height. And so the height measures what we call density. And so again, density, kind of like crowdedness. Like, do you have a lot of individuals that are occurring during that in that bin, or not as many? It's like, how crowded is it? Are there a lot of people for a given width or not? And so it's basically relative to the amount of space in the bin. So like, if you have two bins that are of the same width, if one's taller than the other, that means that one has like a lot more individuals per some unit of space compared to the other one. And so this is why we say like height measures crowdedness, essentially. And so in general, for histograms, you're always going to see that the units are going to be percent per unit on the horizontal axis. So whatever you have on the horizontal axis, in this case we had years, that means that the height is going to be percent per years. And so this is just always going to be the case. And so again, this is just showing that same kind of math of how these are all related. So basically, in histograms, area of the bar is always percentage in the bin, and that equals height times the width of the bin. And so if you want to know kind of how many individuals there are in a bin, you basically use the area. That's going to tell you like what percent of all the data is in the bin, which is pretty much the same as like how many people are there. Whereas if you want to know how crowded the bin is, that's when you use height. So height is just saying like there's a lot of data within some small unit of space for that part of the bin, as opposed to like other bins. So again, just like crowdedness versus just number of individuals. That's the main difference there. Oops, forgot to plug in my laptop into power. Do all the heights add up to 100%? So no, they don't add up to 100%. You can actually just take a look at this. So the height of this first one's maybe around like 1 point something. The height of this one's around like maybe 1.75. The height of this one's like a little bit above 2. So if you add up the heights here, they're not going to be going to 100 necessarily. What goes to 100 is the area. So the area of all of the bins has to go to 100 because that's all of your data is here. So, assuming you're drawing your histogram where the bins cover the range of all of your data, then the area of all of the bars should be equal to 100%. The area is up to 100%, yes. Not just 100%, yes. The area should up to 100% because the area in each bar is in percent. Sorry, just looking through a few other questions. Yeah. So again, like, so some confusion on the y-axis. Why are the numbers so small? Why aren't they actual percents? So again, we want the area in each bar to be a percentage. And we know that the width times the height needs to equal the area. And the width is in years. The width is going to be in the units of whatever variable that you're trying to understand the distribution of. It could be years, it could be seconds, it could be dollars. And so that's always going to be kind of the units of the width. And you know that the units of the area has to be percent. So therefore the height needs to be percent divided by whatever you have on the bottom along the horizontal axis. So in this case, percent per year, but it could be percent per dollars, it could be percent per seconds. But that's kind of why we do it that way. What does it mean when you say the area of each bar is proportional to the number of entries in the bin? So what that means is if there's more entries in the bin, the area will be larger. If there's fewer entries in the bin, the area will be smaller. And that's because the area represents what percent of all the data is in that bin. So if you have a lot more movies in the bin, the area should be larger. Cool. So now that we've seen kind of histograms, and remember histograms are what we use to visualize distributions of numerical variables, it might be nice to actually see a real world example of this. So let's actually do this. So we'll do this with actually a welcome survey that you guys filled out. So the real world example will be you guys. And we'll just try to look at some of the data that we got in terms of the responses there. So I'm just going to read this into a table called survey. And we've put together kind of the responses, cleaned things up a little bit, removed responses that were empty. But we can take a look at what this looks like. So this is the welcome survey. We have a column here on extroversion. So this is how extroverted are you on a scale from, I think it's like 0 to 10. Number of textees is how many people you text on average. Hours of sleep, how many hours of sleep do you get on average? Handedness, are you left-handed or are you right-handed? Are you both, like ambidextrous? Pant leg is a funny one. It's basically saying when you put on your pants, do you put in your right leg first or your left leg? Or maybe you just don't know. And then sleep position. Do you sleep on your back? Do you sleep on your stomach? Do you sleep on your left, on your right side? So we asked this from everybody in the class. And so we'll visualize different distributions right now, just to give you a sense of how we actually can use these charts in practice. So first thing we can do is let's try to visualize some categorical data. So remember, with categorical data, you use bar charts, whereas numerical data, you use histograms. So for categorical data, let's try to look at handedness. So let's say we're curious about what's the distribution of handedness in the class. So one way we can visualize this distribution is in a table form. And so that's using the group function. So for categorical data, we can do survey.group handedness. And then if you want to see what this looks like, you can just type out handedness here. So one question for you guys is, how many people do you think are going to be right-handed versus left-handed? So we have almost like 1,300 responses right now. So what do you guys think? How many people are going to be like right-handed? 94%, 90%, 75%. Okay, at least 1,100 should be right-handed. Okay, cool. Let's check it out. So the person who said at least 1100, that's actually a very good guess. So yeah, right-handed is 1180, left-handed is 99, so around like 10% or so, it seems like, a little bit less than 10%. And then ambidextrous is super small, just 12 people, so very, very small amount of people are ambidextrous. And so again, remember the group function, what it does is it takes all the unique values of this variable, in this case, handedness. So the unique values are just left-handed, right-handed, both. And then it counts up how many individuals have those values. So 12 people are both 99 or left-handed. So group is essentially a way to look at the categorical distribution of your data, but in a table format. If you wanted to actually visualize it in a graph or like a chart format, then you'd use a bar chart. And so we can do that as well. So we can do handedness dot bar h, and then pass in handedness. And so now this visualizes the same data as above, but in a graphical format. And so now you can really see like the difference in the scale. Like right-handed, there's way more right-handed people than left-handed, and then there's very, very few ambidextrous people. So kind of interesting. Okay, so we have that, and then let's try to look at some numerical data. So most of the data in the survey was well, not actually, probably half of it's numerical. So these right 3 columns here are categorical. The left 3 columns are numerical. So you can see that here. And so let's try to visualize some of the numerical data using histograms. So let's look at extroversion. What do you guys think? Like, do you think the class is going to be more extroverted or more leaning towards introverted, or maybe just like split down the middle, 50-50, less extroverts, more introverted? Okay, let's take a look at this. So if we wanted to visualize this as a histogram, we would do survey.hist, and then we pass in extroversion. And so here's what that looks like. So it's interesting, there's like quite a few 5s, but then there's like a lot of people who are 4s, and then even more people who are 7s and 8s. So like that's kind of interesting. So the bump on the right is like a little bit higher than the bump on the left. So there's probably like slightly more extroverted potentially, but it's kind of interesting. How come for this one I didn't specify the bins? That's a really good question. I was just trying to visualize it a little bit quickly just to kind of get the overall shape of it. If I wanted to really look at very specifically, understand exactly how many people are in kind of each value, then maybe I would have specified my own bins. But in this case, I mainly just wanted to really quickly visualize the entire like shape of the data. And so if you don't specify bins, that's a decent way to go about it. But if you actually want to be really specific and know, like, be able to really see like how many people are within specific values and really be able to compare like 2 or 3 specific bins that you care about, then you should specify your bins. Okay, so then we can do the same thing with hours of sleep. So this is a really fun one. So what do you guys think about hours of sleep? Like what do you think like the average hours of sleep is going to be? People, 6, 7, 5. Oh man, let's hope it's not 5. Let's see. Okay, so here we can see like around 6 is a pretty high bump, and then around 7 seems to be where we get like the most number of people. A lot of people with like around 8, and then it kind of drops off after that. Now what's kind of interesting is when you don't specify the bins, Python automatically for you is gonna choose the range of this graph for you. Like I could have drawn this graph from like 0 to 100, right? But Python was smart and it made it smaller. It only drew it from 0 to 12. But if you look at the graph up here, this went from 0 to 10, and we have bars around 10, we have bars around 0. In this graph, we don't see that. So it goes from 0 to 12, but there's no bars around 12, there's no bars around 0. So like, did Python mess up here? What do you guys think? Like why did Python include 0 to 12? Okay, so a few people kind of got Just trying to look through these responses here. Yeah, so that's a really good answer. So someone said there is data, but it's negligible, essentially. So like there is data there, but it's so small that kind of relative to these other bars, um, like we don't have enough pixels to even like draw it, essentially. It's just that small. So like there's maybe somebody getting 12 hours of sleep, but maybe it's like one person out of 1,300. So the percentage is like so small that we don't even have enough pixels to like draw it on the chart. But we can make sure Python didn't just kind of like mess up or something. So we can actually figure out what's the maximum in the survey. So we could do max survey dot column hours of sleep, and so that will just let us take a look at who got the most amount of sleep. So somebody did get 12 hours of sleep in the survey. So that is real. There is at least 112 there, and so that's kind of why Python did do that. Can the range? Yes, the range cannot be edited. If you just specify histogram like this, then it's just going to do the range for you. There are ways that you can kind of adjust the range manually and things like that, a little bit beyond the scope of the class. But kind of another way to do it is just specify the bins yourself. If you specify the bins yourself, then you can also kind of control the range that way. So now let's try to do something a little bit interesting. So let's try to split up the hours of sleep, and look at how it differs based on which leg you put in first when you wear your pants, because maybe there's like some association there. So we can just try to look at that maybe just for fun. So first thing I'm going to do is just make some bins actually, so that we can visualize the hours of sleep a little bit better. Because I want to actually now just make the bins myself, so that when I'm going to basically draw two histograms right now of like two different types of people, and in order to make the histograms comparable, I don't want Python to like choose the bins for me. I want to make sure it uses the exact same bins for both histograms. So that's why I'm going to specify some bins now. So let's go from 4 to 12 in increments of 0.5. So increments of like half hour, because you were allowed to say like 7.5 and 8 in your responses. So we'll make that our sleep bins. And then what I want to do is I want to look at a histogram of the sleep for people who put in their right leg first. So in order to do that, what we can do is we can do survey.where. Remember, we had this function. And so we'll say where the pant leg are containing right. So that's going to basically give us the people who put their right leg in first when they put on their pants. And then once we have that, we're going to call hist on that table. And we're going to do a histogram of hours of sleep. And bins are going to be sleep bins. And then I'm just going to add some code here that you don't need to worry too much about, but I'm just going to add a title to the plot so that you can kind of see it more easily. And then I want to do the exact same thing, but with the left leg. So we have the same exact code as above, survey.where pant leg, but instead of R containing right, we're going to do R containing left. We'll draw the histogram of that table in the same way, and we're just going to give it a different title. So left leg first. And so if we run this, we get two histograms now. Let me zoom out a little bit so you guys can see it. So on the top here, we have the histogram of hours of sleep of people who put their right leg in first, and then we have the histogram of people who put their left leg in first. And so we can try to see if there's any like noticeable differences here. To me, these look like almost identical. But you know, one thing is there's like relatively more people from the left leg who have like this 7.5 to 8 hours of sleep, and same for this bin too if you compare. So these are like a little bit higher than these two maybe, or not higher rather, but the percentage is really what you want to look at here. So the percentage here seems to be larger, like the area larger than this one, maybe a little bit. But basically here is we're able to visualize histogram of like two different subsets of our data set. And so this is kind of one way to do that. So we can see here that doesn't seem to really be like that much of a relationship between which leg you put in first and how much sleep you get. But this is one way that you can kind of assess that. Cool. And then one last thing I want to do is I want to see how many people get at least 8 hours of sleep, because that's kind of like the recommended amount. You should be getting around 8 hours of sleep or so. So we can do that as well. So one thing we can do is, one way to visualize this is we can just bin the data. So we could do survey.bin hours of sleep. And then what we can do is we can just bin this using our own array, where it'll say 0 to 8, and then 8 to 15. I'm just going to do 15 just to be safe. And so if we do this, now we have this table, and what this table is saying is there are 824 people who get 0 to 8 hours of sleep, and there's 467 people who get 8 to 15 hours of sleep. So we can like see that difference right here. So that's one way to kind of get that answer very quickly. So we don't even really need to make a histogram to do this. We can just use the bin function as well, and that just shows it in table form. And so is 8 inclusive? So 8 is inclusive for this second bin, not for the first bin. So the first bin is going to be 0 up to, but not including 8. And then the second bin is going to be 8 up to, but not including 15. So 8 is, if you get 8 hours of sleep, you're going to show up in this second bin here, which is what we wanted. We wanted like 8 or more to be in that other bin. And so now if we wanted to actually calculate the percentage of people who get more than 8 hours of sleep, how could we do that? Any thoughts on how I could calculate, given the data I have above, how could I calculate the percentage of people who get at least 8 hours of sleep? Yeah, so take the number of people who got over 8 hours and then divide that by the total number of people. So we can do that. So 467 is the number of people who got at least 8 hours. And we can divide this by the total number of people, which is going to be 467 plus 824. So this gives us the total number of people in our survey. And so we can run this, and we get 36%. So 36% of people who took the survey get at least 8 hours of sleep. And so one fun fact about this is that last semester, this answer was 31%. And then last fall, the answer was, 28%. So you guys are learning and getting more sleep, so that's really good. So please try to get your 8 hours of sleep as much as possible. It's very good for your health, and not just mental health, but also physical health in the long term. All right, so I think now that we've kind of gone over that real world example, it's probably good to just kind of summarize the main differences between the two types of histogram or distributions that we've seen. So again, we have bar charts, which are the ones where the bars are kind of coming out from the side. And so that's typically going to be a distribution of a categorical variable. And in that case, the bars are going to have equal widths. It's kind of arbitrary how it's made, but they are equal widths. And they're spaced equally. And then the length of the bar, it corresponds to the area, or the length and the area both correspond to basically the percent of individuals that's contained in each category. And then if we have the histogram, that's used for numerical variables. And so in the histogram's case, the horizontal axis is numerical. And then you have these bins that may or may not have the same width. And regardless of that, though, the area is still proportional to the percent of individuals. So that's kind of one thing that histograms and bar charts have in common. The area of the bars is proportional to kind of the number of people or the percent of people that's contained in that bar. But the one unique thing about histograms is that the length of it does not measure that. The length of it measures density, whereas in a bar chart, the length is basically the same thing as the area because everything has the same width on all the bars. So that's what's unique about histograms. Histograms may or may not have the same width, and for that reason, the height doesn't mean the same thing as the area. The height means something else. It means kind of crowdedness or density, as we talked about. So these are the kind of the main differences here. And so to kind of recap all the charts that we've gone over so far, we've actually seen 4 charts so far. So last week we saw scatter plots, which is what allows us to visualize the relationship between 2 numerical variables. Then we talked about line graphs, which is also another way to visualize distribution relationship between 2 numerical variables. But in the case of a line graph, it's more of a sense where, along your x-axis, you're only going to have one value for the y-axis. And so that's why it makes sense to like draw a line through it. If you have any situation where like for one value of x, you could have like multiple values of the y-axis, then you wouldn't really use a line graph. And so that's why typically line graphs make a lot of sense for things like time, where you only have one observation per time, things like that. And then we talked about bar charts. So again, bar charts are for distribution of categorical data. And then histogram is distribution of numerical data. So the thing about bar charts and histogram is that those are just talking about one variable. Whereas scatter plots and line graphs, each of these is going to be like a graph that's talking about two variables and how they're associated with each other. So those are the main differences in all the different charts that we've seen so far. So any questions about this? Okay, cool. So now let's try a quick discussion question. So let's say we have this kind of data. This is like another table that we have, let's say. And so this is showing like daily temperatures. And so we have like different days throughout time. And we have what was the high temperature that day? What was the low temperature? And then what was the condition of the sky? Like, was it cloudy? Was it sunny? And so the question basically is, which type of chart that we just talked about in the previous slide, which type of chart is the best one to use to answer each of these questions? So like, are there more cloudy than sunny days? You know, which chart would we use for that? What percentage of days have a high above 72%? How would we answer that? And then do hotter days tend to also have hotter nights? You know, which chart would we use for that? So think about that for like a minute or so, and then we'll go over the answer. Okay, so let's try to go over the answers here. So for the first one, are there more cloudy than sunny days? So for this one, cloudy and sunny are in this third column here, which is sky condition. And so this seems to be a categorical variable because we have different categories like cloudy, sunny. There's not numbers involved. And so if it's categorical and you want to know, like, are there more cloudy than sunny days, we could do this with a bar chart. So we'd want to visualize the distribution of sky condition. And then we'd see bars for cloudy, we'd see bars for sunny. We basically just need to figure out which one has the larger, like the longer bar. And that's going to answer that question for us. So good job there. Second one, oh, sorry. What percentage of days have a high above 72%? So, you know, 72 degrees, not 72%. So the highs is a column here, and these are all numerical values. So for this one, you know, we probably want to use a histogram. So we could look at the distribution of all the different highs, and then we can kind of get a sense of what percent of the highs are above 72%. And again, one really fast way to do that is if you actually make the bins really simple. So if you just make the bins from 0 to 72 and then like 72 to like 200 or something like that, then you're going to just see basically two bins, and then you can very quickly answer that question. And you can get a sense of like, okay, what's the area of the bin that's greater than 72 versus the bin that's less than 72. So that'd be one way to kind of answer that quickly. And then 3 is an interesting one. Someone said insufficient information. So I always like that answer. Because technically we don't really have enough data. Like, I mean, you could say like, it says hotter days versus also have hotter nights. So technically, if you assume that the high corresponds to like the temperature in the day and the low corresponds to the temperature in the night, then yes, you could use a scatter plot to answer that question. You would just plot highs against lows. And then you can see like, okay, when the days are higher, are the nights also higher? So you could do that. But technically, we don't actually know that for sure. We don't really know if these temperatures necessarily correspond to the days and night. Like maybe the high happens in the day, but then the low might have also happened in the day, and the night was actually like a little bit warmer than that. So a little bit tough to do. It's kind of like a trick question, but you know, if you did make that assumption and you say that, okay, I assume that the high of a 24-hour period corresponds to the day, the low of a 24-hour period corresponds to the night, then yes, you could use this categorical. Cool. All right, so last thing, we probably won't get through all of it, but we should at least get started, is defining functions. So we've used a ton of functions so far, right? We've used like where and sort and select and column. These are all functions that have been made for us by Python, I mean, not by Python, but by other people in Python. And so sometimes there's going to be need to make your own functions because you might want to do your own functionality, and there may not already be some way to do that. So that's where kind of functions come in. And so how do we actually define our own function in Python? Here's how we do it. So first you're going to have this def. This is going to be common in every function. You have to start with this. So def, basically like you're defining a new function, and then you have your name of the function here. So in this case, let's say this is, I want to calculate like the spread of some set of values. And so spread is basically like the maximum value minus the minimum value. So if I wanted to make a function to do that for me very easily, I could define it myself. So you type in a name, and again, the name can be like almost anything that you want. And then you have the argument names here. So you give those a name as well. So in this case, we're going to call the arguments values. And then you have kind of the main logic of your function. Like what does your function actually do? And that's called the body. And so the body can be several lines long. It doesn't have to be just one line long. But it's just kind of what does your function do? And so in this case, this function returns the maximum of the values minus the minimum of the values. And so if your function does return something, then this is called a return expression. And so that's one thing that's kind of interesting about functions. Like they don't have to necessarily return anything, but they might. So they may or may not return something. And we'll see some examples of functions that do things, functions that don't actually return anything. But let's actually go through the process of making some functions. So for example, to start, let's say we wanted to make a function that takes a number and multiplies it by 3. So we could do this. So we could say def, and then let's just call this function triple. And then I'm going to make the argument name x. So again, this x could be anything. You could call it whatever you want, but I'm just going to call it x for my purposes. And then what do I want the function to do? I want it to return 3 times x. So that's the name of the function. And this colon is really important as well at the end here. So you need to have that as well. So you need to say def, the name of the function, what's the argument, or multiple arguments if you have multiple arguments, and then a colon. And then everything after the colon is going to be kind of what is the body of the function. And so make sure you run this line. So now that we've run this line, we can actually use the function now. So we could do like triple of 3, and that returns 9. So you can see that that actually works now. You can also assign a value to a name. So let's say num equals 4, and then I could call triple on that. So I could pass in num, and then that gives me 12. So you can do that as well. And then what's also interesting is that functions are kind of like type agnostic. So Python doesn't know like what kind of type to expect here necessarily. So you could pass in any type you want actually. And some types might work, some types might not. So for example, if I did triple of ha, and this is a string, then this actually works and it does ha, ha. So it actually is able to work properly. Similarly, we could also pass in an array. So for example, let's say we have np.arange up to 4. So this is going to be the values 0, 1, 2, 3. So I could pass this into the function as well. So I could do triple of the array, and then it returns 0, 3, 6, 9. So it multiplies each of the elements by 3. So that's another thing that's kind of interesting about functions in Python. You can pass in kind of any type of value you want. And let's see, let's skip the discussion question because I do want to show you a function with multiple arguments. So let's say we want to calculate the hypotenuse of a triangle. And so we know like the the base and the height. And so if you want to calculate the hypotenuse, it'd just be the square root of x squared plus y squared. So we could actually make a function to do this for us instead of like typing it out again and again. So let's call it, we can do def, and then let's call it hypotenuse. And then this one's going to have two arguments. It's going to have x and y. And then what we're going to do is we're going to try to do this in two steps. So first we'll calculate the hypotenuse squared. So I'm just going to call it hypot squared equals x squared, which is, we used two asterisks to do that, plus y squared. So that's kind of doing this first step here, essentially. And then the final step is to return the square root of that. So we'll do hypot squared raised to the 0.5 power. So that's the same thing as taking the square root. And so now if we do that, now we have a function that can calculate the hypotenuse given the base and the height. So we can do an example like hypotenuse of 9 and 12, and that gives us 15. We can also do 2 and 2, it gives us 2.8. So this is kind of another way to create functions, in this case using two arguments. So just start with a couple questions. Would it be easier to import a function from like another module, like math or something? Yeah, definitely. I mean, if the function that you want, the functionality that you care about, it already exists in a module, you could just import it from the module and use it. And that's kind of, there's examples of that we've already been doing. We talked about how NumPy, for example, has like a lot of functions for us already. Like it has like np.sum, np.max, like things like that work really well on arrays. So we don't really need to make our own functions. We could, but it's kind of redundant. But we'll see a lot of examples in this class where we're going to make functions that aren't available in the module. They're like really, specific to some functionality that we care about. And so not every function that you can think of is already going to exist. So there's going to be many functions that you think of that don't exist yet. Another really common time that we're going to use functions is when we find that we're running the same type of code again and again. So if we're like copy pasting a lot of code and like running it again, but just changing like a few values, and we'll see some examples of that. That's another common case where it makes sense to write a function. Because then, for example, I wouldn't have to write these two lines of code again and again and again. Like, if I wanted the hypotenuse of like 2 and 2, I wouldn't have to, like copy paste this and, do like 2 times 2 and then write it like that. So, and if I wanted to do like a different set of numbers, I'd have to copy paste it again and do like 9 squared plus 12 squared. So instead of like copying and pasting the code, I can just define it as a function. And then it's really easy. I can just call that function with just like a few lines. So it just makes things like simpler. Another good question, could you have done this all in one line? Yes, so you could take everything that I put up there and then paste it down here, and then you could have your entire function in one line. That's perfectly fine too, but a lot of times it's preferred to split things over multiple lines. Again, just so it's like a little bit easier to read, you're probably less likely to make a mistake in the code, like, like type something incorrectly. So it's often a good practice to split things into multiple lines. And then the 0.5, why did we do that? So we raised everything here to the 0.5 power. That's the same thing as taking the square root. That's why we did that. Is there a limit to the number of lines that this can take? There's no limit, actually. Your function could be very complex and it could do like a lot of things. And we'll see more examples of that. We'll have functions later on in the class where it's like 10 or sometimes even like 20 lines of code. And that's fine. So you can have functions. You probably don't want to write a function that's like 1,000 lines of code because you do want to make the function easier to read. And so, there's like a best practice, I guess, around limits, but technically there's no limits to it. And yeah, let me switch this back to the way it was. Cool. So we're definitely over time. I'm just going to stop the screen share, but I'll stay on to continue answering questions though.